All right, well, the next section that we're going to talk about deals with unintentional islands. We're going to look at a case where we're going to take a section of the system that's got its own sources and loads and cut it off when we don't want to. So did anybody have any questions before we got launched back into this? Everybody got your coffee so you can stay awake after lunch? This is always a tough time of day to stay going.
I did have one quick question.
Yeah.
For a lot of these problems you've been describing, at what relative size to the system is your distributed generation compared to your substation transformer? Where did these issues start to appear?
That is an excellent question. I'm actually going to show a slide that talks about that for low inertia systems specifically. But for distribution feeders, usually it's kind of a circular situation because the definition of high penetration on a feeder is that penetration level at which mitigation starts to become necessary. So, thanks a lot. Usually, I'd say when you start seeing when you get to the point where you start seeing reverse current flow on any subsection of the system, that's where you begin to see impacts. You'll start to see them in that section first, but so you can start breaking it down, by that way. So really, what it boils down to is relative to the minimum load. Anytime the generation starts to exceed the minimum load, you will start to see some impacts. You may not need mitigation yet, but usually when you're below the minimum load, the impacts are so small that it disappears into the variability of the load. But above that is where you start to kick in.
Thank you.
Sure. Any others? All right, I'll try to be a little less of a lazy bum and actually go ahead and stand up, so I can prevent this from being the first time in which I fell asleep during my own presentation. All right, well, unintentional idling, what the heck are we talking about? Here's our feeder again. Once again, for some reason I don't have a tap changer in here, but we've got a set of distributed generators, which I have marked as PV. Loads, there's a variety of capacitors and switches and things in here. And you notice there are, I guess on this specific circuit, there are 3 different switches, which are the ones that are marked there with the arrows, where we can isolate sections of the system. So let's assume for just a minute that I'm going to open that recloser R1 for just a minute. When that happens, what if I have a case where the PV plant out there happens to be producing the same amount of power as was required by loads 5 and 6, and that capacitor C2 was producing the amount of Rs that was required? So basically, excuse me, I have a power match in both real and reactive power inside the island. When I open that recloser R1, I didn't interrupt any current, right? There wasn't any power flowing through there, real or reactive. So when you open R1, nothing happens, and the distributed generator really can't see the difference. You get current coming out of the DG that goes into the loads, and by Ohm's law, you get back the voltage that the utility would have produced. In that case, where you've got a very close match between the real and reactive power sinks and sources in the load, in the island, then islanding can be a little bit difficult to detect. By the way, I should have defined that at first. An island is just a section of the system that's got its own sources and loads. So an unintentional island is one where we didn't intend for that to happen. We opened a switch, but it wasn't supposed to stand alone. So this case that we're talking about here is a case in which I can form an unintentional island, but the voltage remains enough like the utility voltage was that it's really hard to see. I would point out that if I open, say, that sectionalizer S1, it would be nearly impossible to get an island to form out there because, as you notice, there's no VAR source. If I was operating the PV off of unity power factor, I suppose I could, but almost everything in the system is inductive, so something's got to be source and VARs, and the closest capacitor is upstream from that sectionalizer. So this would be a case where I wouldn't even worry too much about sectionalizer S1. You're not going to get an island there. How have we dealt with this? The industry has been aware of this problem for many, many years. Over the course of those years, a number of solutions to the problem have been developed. We started off historically with passive methods, which are pretty much exactly what the name implies, that we're monitoring the terminal voltage and looking for some condition that indicates that an island has been formed, and then the distributed generators can trip offline. Or you could go into a microgrid mode, whichever was appropriate for your circumstance. These passive methods, remember that we talked before about one of the things that we want inverters to begin to do is to take on a grid support role. So we're trying to add grid support functions into the inverters, things like the volt-var characteristics that we saw. And remembering that the main purpose of those grid support functions is to help to stabilize the grid, help the grid to work better. So whatever loss of mains detection method that we come up with, we want it to be compatible with these grid support functions. The passive methods turn out to be very compatible with grid support functions because they don't really have to do anything with the output. We're just monitoring. So it doesn't really impact that. And the cost of implementing these is relatively low because, again, it's just monitoring and signal processing, which we have to do anyway to operate the inverters. The problem shows up in the middle column there of effectiveness. For every passive method that you can put into an inverter, it is possible to come up with some kind of system condition or some type of load that undoes whatever it is the passive method is looking for. We refer to that as a non-detection zone. So all of the passive inverter-based methods have non-detection zones. Some of the non-detection zones are fairly small, and you can use more than one passive method to look for non-detection zones that don't overlap. But generally speaking, like this balanced case that I talked about, no matter how good your passive method is, if I balance the generation and load close enough in the island, the voltage doesn't change, and you can't really see it. So the passive methods eventually gave way to these active methods here. Active methods essentially are kind of the next step in the evolution that we said, okay, if there is a small change in the voltage or frequency, act in such a way as to try to make that worse, basically lean on the grid and see if you can move it. So really the hallmark of the active methods is positive feedback. We have positive feedback that looks for some small error and then acts to make that error worse. Usually it's an error in frequency. And I mentioned before we had an impedance detection method before. That also would have been an active method. But there's one called the Sandia frequency shift, where it's just a straight gain on the frequency error. As the frequency starts to deviate away from where you expect it to be, start applying a little bit of a gain to the phase and see if you can push it further away. And at some point, the inverter says, I shouldn't be able to do this, and it turns off. The active methods have been very, very effective in detecting islands, because what they do is they break up that balance. Any tiny little error that we see is caught by the positive feedback and then driven to a trip point. So they work quite well. In terms of cost, they're really not much more expensive than the passive methods. I increased it a little bit because obviously we have to do something to power quality to make them work, but it's not prohibitive in any way. But the problem is this compatibility with grid support functions. I mentioned before that the grid support functions are trying to stabilize the grid. Well, what did I just say active anti-islanding is trying to do? Trying to destabilize the grid. So generally speaking, there is some conflict between these. And not only that, there's a penetration level issue as well, that as we start to get lots and lots of distributed generation in the system, the last thing you want it to be doing is doing this with the frequency of the grid all the time. So ultimately, as we start to see more and more of this, and as utilities may eventually start to become reliant on it as a source, we need to move past active anti-islanding to something new. The last category, the last row that's shown here, are these communications-based methods. Basically, we just have a comm signal from upstream on the system, from outside the island someplace, that is telling us what is going on, and then we just respond to it appropriately. The prototypical communications-based method is direct transfer trip. There's a comm link to the feeder breaker that says, I'm open, I'm closed. Simple enough. The communications-based methods in general are very, very effective. And they have excellent compatibility with grid support functions, because if I'm trying to stabilize the grid, I can still tell whether the feeder breaker is open. The problem with the communications-based method is the one that we're all aware of. It's the cost. The comm channels, yeah, several people are doing this. Comm channels are very, very expensive. If I wanted to do direct transfer trip to a feeder breaker, for example, then I can't just walk into the substation and stick a wire on the breaker. Right? There's a bunch of substation engineering. There are a bunch of requirements that need to be met. And you might imagine there could be more than one switch. I showed in that circuit there was the feeder breaker, a recloser, and a sectionalizer. What if that recloser were, say, a pole top recloser, and I needed to get direct transfer trip to it because there was a risk of islanding downstream? It's logistically very difficult to do DTT on a pole top recloser. They're generally not equipped for it. There's no COM port or anything. They're outside the secure perimeter of the substation, so there are NERC-FERC issues that come into play. So it can be kind of a tricky thing to do. When do we and don't we worry about islanding as an issue? I mentioned one case a minute ago that, as we've been discussing, you have to have a match in both real and reactive power in the island in order to have any risk of islanding at all. So the first one we look at is if you don't have a VAR source. If there aren't any capacitors, if there's not something sourcing VARs. Now, remember, this could be underground cable too. But if there's not some capacitive source there, you're not going to get an island. What happens, as I mentioned before, is that when the island forms, the inverters are cruising along producing their output current, but then the voltage will jump to the new phase angle because the load is inductive. If there's no VAR source, then the inverter will start speeding up its frequency to catch up. Of course, the frequency goes up. That kicks the anti-islanding in, and out she goes. So if you don't have a VAR source, there will be a frequency deviation that could be detected, and it's not going to be an issue. So where do we start to get concerned? There are really two main cases that we worry about. I've subdivided one of them into two. That's why there's 3 bullets here. The first one is that if you have a mixture of different inverters in the island, it says different manufacturers here, but what it really is different product families, different types of inverters using different anti-islanding. The reason I throw that caveat in is because you can have inverters from the same manufacturer that might actually be made by different entities, so they may be using different anti-islanding. But if the rule of thumb that we use is if there's no single product that accounts for 2/3 or more of the aggregate DG on the feeder, that's when you start thinking, okay, we should look for an interaction between things here. In most cases, it's still not a problem. Most manufacturers' products actually play with each other pretty well. But there are some notable exceptions, and you just have to watch for that. One other problem that we end up with is when you have a mixture of rotating machines and inverters. And the reason is because, as we said before, the inverters generally are trying to push frequency. The sync gen will be trying to stabilize frequency. The sync gen is trying to move the voltage. And the inverters, again, are not participating in that, so they'll hold the voltage relatively firm. And the two counteract each other. They can't see what's going on. So having cases of mixtures of rotating machines and inverters is the other real case that we worry about. I mentioned this new market entrance. Really, that one is kind of a subset of the multiple manufacturer case. Even if with a new market entrant, if their inverter is listed under Underwriters Laboratories 1741, UL 1741, the tests in UL 1741 are derived from the recommendations in IEEE 1547. So 1547 and 1741 are closely linked. 1741 includes an anti-islanding test. So if you've got just one manufacturer's product, even if it is a new market entrant, if it's UL listed, probably going to be okay. Because again, with single manufacturer's products, as long as there's anti-islanding in it that works at all, probably going to be all right with the way modern anti-islanding is. But if you've got any of those with existing inverters, you got to find out what's going on with the island detection. Make sure that this isn't an issue where things are going to adversely interact with each other. Inversely interact with each other. Interesting. And I mentioned this before, that the risk of islanding does rise as we start to add grid support functions. And we've been doing quite a bit of work on this with Sandia National Laboratories. It looks like this issue may be less of a concern than originally thought, because there's still enough of a destabilizing effect from the positive feedback that even with the grid support functions, once the grid's not there, the grid support functions can't overcome the positive feedback of the anti-islanding. So we're still seeing most of the time anti-islanding is still remaining effective. I haven't seen a case yet where a 1741 compliant system became non-compliant just because of activating the grid support functions. I do understand that such cases have been observed in the lab, so it can happen. But the bottom line of all of this is that we do know the risk of islanding, the effectiveness of anti-islanding decreases when we add in grid support functions. I want to show you a couple of cases. These are specific case studies that we have worked with at NPPT. What you're looking at here is, you can think of it as a thermal plot. It's a surface plot, but you're looking at it straight down the z-axis. On the x and y axes down there, you see it says load fraction and power factor. And you can think of those as basically being the real and reactive power mismatch. And then you see there's a color scale that talks about the run-on time. The z-axis, or the color scale, is the run-on time, which is defined as the length of time between the formation of the island, opening of whatever the switch is, and the detection of the island by the inverter in the shutdown. What you can see here is that there's a ridge there of slightly elevated run-on times. And that's basically where we have the best matching, the best balance. Outside of that area, the run-on times are very, very short, like maybe 250 milliseconds or less. On that elevated region there, about 360 milliseconds is the worst that we see. And bear in mind that the IEEE 1547 recommended maximum run-on time is 2 seconds. So this is compliant. There's no problem here. No risk, no need for mitigation of a risk of unintentional islanding. This case, I may mess this up. I'm trying to remember how all these cases fit together, but I believe this one was a case with two PV plants on the feeder, no rotating machines, and it was 2 different manufacturers, but they were using approximately equivalent anti-islanding methods. So even with the 2 inverters and several inverters on the feeder, no issues. They saw it just fine. So this is a case where things worked the way they were supposed to. Here's a case where they didn't. You see the red. Everything that's red is a run-on over 2 seconds. This is a case in which we had, again, trying to remember this correctly, 3 inverters, three PV plants from 3 different manufacturers, and a synchronous generator at a landfill gas-based plant. And the issue that we ran into was one of the inverter plants was a new market entrant, and the synchronous generator plant had pretty minimal relaying. And there were cases in here in which we could get islands that were effectively stable. It would run on until something else happened. I point this out that one of the things that people will often say is that, well, what is the likelihood that this is going to happen? That, the island would stabilize like that because the load is going to change and stuff like that. And people who make that argument are absolutely correct. I think islanding is a pretty low probability event. The likelihood of getting and maintaining the level of matching required to have an island is pretty low. The thing is, the way the standards are worded right now, it is the responsibility of the distributed generator to detect and prevent that condition. So you can't rely on the load. If there is a case where you couldn't see the island, then the distributed generator has failed in its job. And of course, it becomes a risk mitigation issue too. Obviously, you can't reduce the risk to 0, right? There was a risk involved in walking down the hall from the cafeteria back to this room. So I'm not sure what it was, but there probably was one. So we have to be reasonable about this, is the point that I'm trying to make. So in this case, because of the interactions between the different generators, the active anti-islanding in the inverter plants could not see the island, and it ran on for a long time. So this was a case where direct transfer trip would have been required. And the way it works then is the last guy in pays for the direct transfer trip. So there were 2 PV plants in the sync gen that were all grandfathered in. When the 3rd plant came in, that's where this study got triggered and they got flagged. How do we deal with anti-islanding today? Well, I mentioned this, that almost all commercial inverters, not all, almost all, use active anti-islanding with some form of positive feedback in it. And when they use that, they are very effective in determining when an island is formed because they destabilize that island. I mentioned this before, that Underwriters Laboratory 1741 has an anti-islanding test in it. The test involves using an RLC circuit that is tuned to resonate at 60 hertz and has a quality factor of 1. And the idea, there was a lot of research done in the late 90s. This actually was part of the subject of my doctoral thesis, where we were looking at what is the worst case scenario, what messes up anti-islanding the worst. And it turned out that it was this RLC circuit because effectively it's like an electrical inertia. As the inverter is trying to move the system state, that load is ringing at 60 hertz. So it keeps kind of trying to pull the frequency back. Excuse me. The quality factor of 1 was kind of it's not an arbitrary number, but we were looking for a realistic worst case value. And the first number that back in the early days of this standard, the value that was used was a quality factor of 2.5. And the standing joke was always, why 2.5? Because it's half of 5. Whatever. It became clear that a quality factor of 2.5 wasn't realistic. We don't have distribution circuits with quality factors of 2.5. So that's why this got dropped back to 1. If we see a case where the anti-islanding is insufficient, right now, today, normally what happens is we'll require direct transfer trip. So I've said several times, active anti-islanding is quite effective in preventing unintentional islands in distribution feeders. So why are we talking about it? Why is islanding a concern at all? The reason is because as DG penetration levels are rising, we're starting to see more of those problem cases we identified before. And also, as I mentioned before, we want grid support functions. So we're basically trying to make the system do some of the things that we've already identified as a problem. So in order to make sure that the risk of islanding doesn't rise when we do this, we are eventually going to need to get away from the way we've done islanding today and look for new means of doing this. The active anti-islanding is going to be good for a little while yet, but like we said, as the penetration levels get high, you don't want all your distributed generators doing this with the grid all the time. So what are we going to go to? How is this going to work? And I think there are, the main category is probably going to be these communications-based methods. We talked about that before, that they're extremely effective. The key is, can we find a way to do COM-based anti-islanding that is affordable, that's cost-effective in this application? There are two main methods that I am particularly interested in that we've been working on for quite some time. I'll start with the bottom one first. It's power line carrier permissive. You all know what power line carrier communications are. I'm sending my COM signals over the actual phase conductors. We've done that forever at transmission. There's a little bit of it in distribution for AMR and some other kinds of things like that. We have used power line carrier signals like this to enable anti-islanding functions. And what you need, more than anything, is you need a continuous carrier. As long as there's always a power line carrier signal there, we can use the presence or absence of that carrier signal to tell me when I'm still connected to the substation. So this method is extremely effective. It works very well. And you remember I mentioned that you can have more than one switch in the circuit. If I put a signal generator in the substation, all the series switches on the circuit are all instrumented already. So there's some very nice things to recommend power line carrier. That coupled with the fact that it's just very intuitive, right? It makes a lot of sense that this is kind of the way to, the inverters are not going to reproduce the power line carrier signal. They may reproduce the 60 hertz, but they shouldn't reproduce the COM signal. We have worked a lot with subharmonic power line carrier for this application. We used Hunt Technologies' Turtle system for a while, demonstrated that it worked for this. There is a high-frequency solution also made by a company called Grid Edge Networks that is very intriguing because it's got a different cost trade-off. The problem with the subharmonic systems is that the signal generators are very expensive and require a lot of substation engineering because they're big and they have to go in the substation. The high-frequency system that I was just mentioning a minute ago has a different cost trade-off. The signal generators are much, much smaller, much, much less expensive, a lot easier to install in a sub. But because it's high frequency, there's a propagation trade-off. So they have to have some downstream repeaters and other things to get around transformers and stuff like that. So it's a different market participant there with a different cost trade-off. It's going to be intriguing to see how this works out. The other communications-based method that I've got up here is based on synchrophasers. I'm going to assume that most of us are at least tangentially aware of what a synchrophaser is. You know, a phasor is just a specific voltage measurement, right? Angle and magnitude. Or it could be a current measurement as well. All a synchrophaser is doing is taking a bunch of phasor measurements from different places and then putting a GPS timestamp on them so that we know exactly, this measurement was made at the same time as this measurement. We can time align them and get a picture of what the system looks like. all at one moment in time. My company has been working on a number of different synchrophaser-based methods, but the one that is kind of my favorite is we use the frequency that's measured by two phaser measurement units. One of them is outside the island. It's upstream on the system someplace. And then that PMU is broadcasting the frequency measurement downstream so that it can be received by the distributed generators. The DGs have their own PMU there on site. They receive the remote signal. They do their time alignment. Then they do some kind of a comparison to figure out what their status is relative to the rest of the grid. And the one that we are using, actually, we're just looking at a statistical correlation between the two frequencies. If we're grid tied, then locally the frequency should track pretty well with the grid because that's a universal parameter, right? It's pretty much across the whole system. As soon as the island forms, the frequency controls, such as they are independent in the island versus on the grid, and the correlation goes away. So this method has actually worked extremely, extremely well. As I've talked about this in past versions of this presentation, we need, for anti-islanding, we need the same 3 S's that you need with every other part of protection. You need speed, sensitivity, and selectivity. What we have found with some of these methods, of course, cost effectiveness too, but that doesn't start with S, so I'm not going to talk about it here. The synchrophaser-based methods, we've had very, very good sensitivity and selectivity. What that means is that this correlation-based method that we talked about doesn't miss islands. It is very good at catching islands. It's also very selective. It doesn't false trip when there isn't an island. For example, if there's a loss of generation, the frequency dips on the system, if we have local switching events, this method has worked very well in all those cases. Speed has been the problem. It usually detects within 2 seconds, but not always. It's a statistical method, so the run-on times then vary statistically. We're working on that to try to improve it, so that's kind of where that work is at this point. But the beauty is there are some communications channels, some broadcast comm channel possibilities that might make the synchrophaser-based approach one in which the communications costs can be significantly reduced. So again, a lot of promise in both of these methods. It's not clear at this point which one is going to be the market winner, if you will. And there are people actively working on both. The bottom few bullets here, okay, now what happens when the comm channel, when the communication signal fails, when I lose my comm signal? Because it's going to happen, right? I need some kind of a fallback. And we've said a minute ago, it really can't be active anti-islanding because we need to get rid of that in order to be able to meet the other goals that we have for the system and for the distributed generation. So, well, the only other option is we go back to the passive methods. I think this is probably going to work out okay because basically what you do is you think of the passive methods as being like zone 2 protection. We all know that zone 1 is the one we rely on. You fall back to zone 2 if something's wrong with zone 1, but zone 2 is as good, right? There may be some little holes in zone 2. It's the same thing here, right? We can, by using combinations of the passive methods, we can make those non-detection zones small enough that it should be sufficient as a zone 2 method. One thing that I would point out is that with power line carrier permissive, we actually can't use a fallback because it is the loss of the comm signal that determines when the island has occurred. So that puts some reliability constraints on the equipment. Excuse me. So, any questions on unintentional islanding? All right.
Is there a load difference that you know will cause it to trip out? So if you got a 100 kW or DG and you're at 98 or 97, is that enough for that to trip out, or has there been any work on that determination, what the difference would be?
Yes, there has. We actually have a paper that I co-authored with some folks from Sandia National Labs. That's a guidelines document that looks at exactly questions like that. So I'll tell you what, whoever asked that question, would you please drop me an email after this? I'll send you that paper.
You can send me
I can send it to you. Okay.
and if you want to let me know, I can hook it up.
So we have done some work on that. Basically,
I'll share it with the group.
that'd be cool. It's more sensitive to a VAR mismatch than a watt mismatch. Generally speaking, if you've got an active anti-islanding method in there, you got to be matched to much, much closer than 1% in order to get enough of a match that the active anti-islanding wouldn't see it. And that's why we've said before, I mean, really, this is a very low likelihood event. The probability of getting that close of a match and keeping it for any period of time is very low. It's less sensitive in real power, so you might be able to be off by 5 or 10% in real power and still not reach the trip threshold that would be triggered by the real power. So I'd say, maybe on that order of 5 to 10% in real and less than 1 in reactive.
So if I've got let's say it's an overhead feeder, and I have no caps on that feeder, I wouldn't have to worry about islanding.
I would say you're free and clear. You can't get a VAR balance if there's no VAR source. And if your load is strictly inductive, once the island is formed, the frequency is going to take off. It's going to go up, even without active anti-islanding. But add the active anti-islanding in there, it's going to go up that much faster. So, yep, if there's no VAR source, no caps, you're probably home free. Cool. Does that answer both of those questions?
That's for inverters.
Yes, that is for inverters.
So for like doubly fed induction generators, has there been work on that? I mean, they can vary their bars fairly easily.
Yeah, that's a great question. And as we mentioned before, doubly fed induction machines are kind of a curious mix of inverter and rotating machine behaviors. We have seen some cases where they tend to run on more readily than strictly inverter-based units, because what can happen is that the positive feedback anti-islanding is trying to move the VARs in one direction or the other. The transient VAR demand of the machine tends to go in the opposite direction. We see this a lot with like the self-excited machines, but it can kind of be self-defeating if you're not careful. So I don't have the same numerical guidelines for you on like a Type 3 wind turbine, and I apologize for that, but they would be wider than would be the case with a strictly inverter interface source.
My mic was off a little bit earlier, and I mentioned that Mike emailed me that Sandia report, and your name is, so I can make sure that you get that.
My name's Mike Graves. Graves.
I'll get that to you.
Cool. Good questions. Any other questions? All right. So let's move on through here. Oh, we're getting quite short on time, so let me see if I can cruise through this just a little bit. I did want to talk just a little bit about resiliency and the use of distributed resources to help improve resiliency through the application of microgrids. And we've all heard this term microgrid. It's become the buzzword of the week in our industry. For us, what we're going to say is, basically a microgrid is an island that we can island intentionally. It's as simple as that. Microgrids, by definition, have a grid tie. If it's like a standalone system that is always off grid, we just call that a low inertia system. Microgrids generally are low inertia, but not all low inertia systems are microgrids. I talked about this way back at the beginning, that the concerns about system resiliency have really risen lately because of some of the impacts of some of the big storms and other things that have happened to take out wide swaths of the power system. I was at a conference up in the Northeast not long ago where we were talking about microgrids, and they tell some absolute horror stories about what happened during Sandy. And they have medical facilities that have lost power trying to move patients down the street in the storm to a facility that might still have power. First responders couldn't recharge their communications. Even if you had like diesel gen sets, you couldn't deliver the fuel because the streets are all strewn with debris. So it was a big deal. We, in our part of the world, have been hurricane free for quite some time, but we have things that look like this, right? So I mean, there are disasters of this type that affect all of us. I still haven't figured out exactly how to harden the system against an earthquake. I don't know what you do when the ground moves. But I said we could suspend the system in the air. Wireless power transfer. There it is. Anyway, the bottom line is that we as a society are critically dependent on electric power, and the reliability of that power is becoming more important all the time. So we want to be able to use our distributed resources to try to enhance resiliency and reliability. I won't belabor this point. You guys know about the reliability indices that are used. But what I did want to point out is that the first thing that everybody says is we'll move the system underground. Right? You think about that, especially looking at that ice storm picture. Undergrounding of feeders will help improve the frequency indices. It will make outages less frequent because we have trees hitting lines and things like this. But it will increase the duration indices because it takes longer to find and fix the problem once it happens. So they're good, but that's not a silver bullet either. I mentioned Flizzr. Flizzr's great for local events, but for widespread events, my adjacent feeder to which I have the normally open ties probably on the ground too. So again, that doesn't help for things like this. Having sources close to the loads is going to be an important part of the solution. And ideally, these sources would be able to automatically reconfigure so that the biggest part of the system possible can be brought back up and kept energized. Now, a lot of things about microgrid design are not new. Right? You all recognize this as a Generac diesel. This particular one is at the National Renewable Energy Laboratory's test facility outside of Boulder. But we've had standby and backup power supplies forever. So most of these are small engine gensets, maybe natural gas powered, so that you're actually working with two grids. The power grid fails, the gas grid hopefully is still there. Gives you a little bit more reliability, but most of them have a transfer switch. It may be automatic, but it's not seamless. So you'll transfer from the grid to off grid with maybe 30, 40 second blackout. If you need a seamless, or what people tend to call a blinkless transition, then you'll put a battery in there that basically acts as a UPS to ride through the period between having a grid there and having your engine genset up and running. You notice I define need on this slide. That very few customers actually truly do need blinkless power. There are some who do, right? 911 call centers and things like that. But, having to reset the blinking dial on your clock is probably not going to justify the cost of a BIS. So a lot of customers really can tolerate a short blackout. I was just going to say that you have to be a little careful. A lot of people assume that if I black out the system and then restart, that simplifies the design. Yes and no, because does it mean I don't have to handle the seamless transition? Yes, but now I got a black start. So there are considerations both ways. So, and I mentioned this here, that for the most part, backup power systems assume that I've got a single source bus that's going to dominate the microgrid. Then grounding is per IEEE 142, and the grid interactivity, if there is any, is completely commanded by the host utility. Get online, get offline, provide these services, whatever. It's all driven by the system operator. So what's happening now is that we are violating all those assumptions. We want to create a system that can reconfigure itself, and where the intelligence is sufficiently distributed that there's no single point of failure, that will keep as many people up as long as possible, no matter what is happening on the system. And I didn't specifically say this. I mentioned natural disasters. We could have man-made disasters too, right? Somebody parks a pickup full of explosives under one of our transmission lines or something. So when things like that happen, we want the system to be able to take itself apart and reconfigure itself. And then we can figure out what happened later and re-optimize it. But keep people on for as long as you can. So we've got these much more complicated system topologies. We don't have a single dominant source. There isn't a single source bus. Widely varying characteristics between the different sources. So it's a system that has just become considerably more complicated. And when this happens, the system integration, the controls design are absolutely critical. And you really do need a lot of modeling and hardware in the loop simulations to deal with this. We've talked about this before, that what the transient simulation gives you is a virtual laboratory. It's a means for improving your understanding that is non-destructive, maximum safety, minimum cost. That's what it's for. And that's the kind of modeling that we do at our company. Hardware in the loop simulation then is I can actually test real controllers with a simulated power system. And that can be valuable for bench testing, functionality testing, that kind of thing. We test relays that way. There's such a thing as power hardware in the loop simulation, where we actually are simulating you've got the actual inverters in there, and only the power system itself is simulated. We can't do that. We don't have equipment big enough to do that. They can do it at the National Renewable Energy Laboratory. So do you need energy storage in a microgrid? It really depends on your objectives. A BIS can buy you a lot. It can give you the seamless on-grid to off-grid transition we talked about. You can accommodate much more distributed renewable resources into your microgrid if you do that. It can improve reliability, but you've got to be careful. Battery inverter systems, as we all know, are extremely expensive, and particularly over the life cycle, because you'll have to replace the batteries probably a couple times during the life cycle of the system. That gets very expensive. But one of the things that we find is that the controls design and the system sizing are often oversimplified. And the problem then is the nightmare scenario. You can end up spending a lot of money and get a system that does not do what you intended for it to do. So again, you want to make sure that the design process is done correctly. And modeling is a good way to get a start on that as well. I'm going to really quickly walk through one case study, which is a system we worked on not so long ago called the high reliability zone. This is a feeder that is going to be turned into a microgrid. So we're going to be able to intentionally island an entire distribution feeder. About 5 megawatts worth of load, approximately 5 megawatts worth of diesel generation in certain critical facilities already existing on the feeder. The objectives of the project were we wanted to be able to do a seamless on to off-grid transition. Part of the reason for that was because on this feeder there was a prison, the city 911 call center is on here, there was a military facility, all of whom have a legitimate need for blinkless power. And we keep laughing that the one that really needed the blinkless power was the state lottery computer center was on this feeder. But then we want to be able to basically increase the reliability of service, right, is the entire key of this. Our roles, we did a bunch of system-level modeling. We designed the BIS controls, did some tuning of the generator controls. We supported design of a load shedding scheme. We didn't actually end up using it in the fielded system, but we did have one design. And then we did a lot of test plan designs. I talked about before about a lot of what we do is in the proof of concept. So did a whole bunch of design of tests and requirements documents and that kind of thing to make sure that the system ultimately was going to do what the client wanted it to do. So we had said before that they wanted us to have a seamless transition. What is a seamless transition? How do you define that? What we did is we used the CBEMA curve again. We fall back to that same acceptance criterion. For the voltage, we're going to stay within the CBEMA limits, and for frequency, we're going to stay between the IEEE 1547 limits, which is 59.3 to 60.5 hertz. The way we're going to do this, the key to doing this, is the fact that the BIS is so much faster than other system components like the generators. So the BIS will jump in quick. It's got to have enough power to support the entire feeder, but just enough energy to keep the feeder up while the diesels get started. Once the diesels are on, back the BIS out, and then the diesels pick up, and the system will continue to run that way. Here's a model of the system. We did all of this in MATLAB Simulink. All the controls design, the system modeling, everything was done in the MATLAB Simulink environment. I mentioned before about 5 megawatts worth of diesels. You see the DG sites, the diesel sites, are all indicated by the arrows there. There was a desire to add as much as about I said 25% penetration here. The number that sticks in my head is about 2 megawatts of PV that they wanted to put in this 5 megawatt microgrid. So that's closer to 40% penetration. And as I said before, we ended up with about a 5 megawatt, 1.25 megawatt hour BIS to do this job. 5 megawatts because, as I said before, when we first start the HRZ, the BIS has to pick up the whole load. So it's got to be sized accordingly. In power, in energy, if you time that out, a lot of people look at that and say, what is it, like a 20, 25-minute battery? It's actually about a 12-minute battery. When you take into account the minimum charge constraints, the current constraints on the inverter as the DC bus voltage drops as the batteries discharge, about 12-minute battery is what we got. Now, it turns out that's plenty because we can get these diesels up and ready to go in about 6 minutes. So we're in pretty good shape. But the reason I bring that up is because just straight back of the envelope calculations would give you the wrong answer about how long this battery is going to last in the system. And if you designed it too close to the edge, again, you get a BIS that costs you a fortune and doesn't do the job. When we did the controls design, the key was speed to be able to do that seamless transition. That was a real challenge because we've been saying all these inverters are current sources when they're on grid. When you go off grid, it has to be grid forming. So you're going to go into voltage and frequency regulation mode. When we had the mode transition, we got from current source to voltage frequency source, couldn't make the seamless transition. So what we did, we knew off grid it had to be droop controlled, multiple independent, small, non-dominant sources. That's really the only choice. So we said, well, let's make it droop controlled on grid. And we manipulated the droop slopes and the droop parameters to set it up so that it looks like a current controlled system while it's on grid. That system actually worked really, really well. We were able to get the seamless transitions, which I'll show you here in a minute. Here's a case, one particular case where the system's cruising along fine, then at 4 seconds, we get a step change in the voltage down to 0.7 per unit. At 5 seconds, the HRZ is commanded to jump ship and take care of itself. So you notice the top plot there, you see the BIS output power. That's the one where there's a big jump upward at 5 seconds because the BIS is picking up both the real and reactive part of the load. The model here is a ZIP motor load. ZIP is constant Z, constant impedance, constant I, which is current, constant P, which is power. And then the motor part, we explicitly modeled both single and three-phase motor load in this island because it's important to get the dynamics right. You'll notice that as the BIS is picking up the load, there's a little bit of a transient there. It takes a little bit to get it all the way up there. That's a motor start, right? Where we had sagged down to 0.7 per unit. There was basically almost like a fault-induced delayed voltage recovery there that the BIS had to get us over. So that's what that is, and that's why getting the motors in there is important. You see there's a little bit of a blip in the power going to the loads, but it's fairly minimal. The BIS picks it up pretty smoothly. Bottom plot is the frequency. Remember that we wanted to stay between 60.5 and 59.3, and as you can see, we did that handily. One thing we did have to watch for is, if I remember this right, one of the generator plants had a Rokoff relay, rate of change of frequency relay on it. These frequency rates of change were a little fast, so there were some adjustments required to make sure that generator did not open its breakers and become unavailable to the HRZ right when we were trying to go off grid. So, but that was a solvable problem by changing the settings. And here's the voltage. We show that the frequency stayed in spec. Here's the voltage relative to those C-BEMA curve limits, and you can see we managed to stay within pretty handily. You notice the one green dot that's on the blue line? Remember that the time violation is actually over there 1 second, and we're well to the left of that. So we're comfortably inside the C-BEMA envelope. So again, the bottom line is that keeping this thing in droop mode all the time worked, and the use of the simulation engines to design the controls allowed us to come up with an effective solution. Here's another use case, and these are in your slides. I'm not going to belabor the point too much because we're going to run real short on time, but you can see here the same deal where we go to the microgrid mode, we hand off control from the BIS to the generators. Then you'll notice that the BIS stays in droop mode while it's recharging. So it's a controllable load while it's in recharge mode and is still helping to regulate the microgrid. Then at 25 seconds, we kicked this thing in the teeth. We doubled the load. We did a step doubling of the load, switched in a whole bunch of impedances, constant power, and motors, cold start. You can see that there's a frequency blip there at 25 seconds in the bottom plot. And I will admit that you notice there's some fast oscillation in there. That was because at the time that we made this plot, the tuning of our BIS controller wasn't quite right yet. So that's a defect in our controller, which again is solvable, but you can just kind of see that there's a lot of work involved in doing this. But we did stay within the frequency bounds. Here's the voltage. Now you can see this time we were not able to stay within the voltage limits. Where we dropped out was that case where we step doubled the load. We did cases where the load wasn't doubled. We did a 25% step and a 33% step. And the system rode through both of those without a problem. The utility said, what's the likelihood of a step doubling of this 5 megawatt load? It's not going to happen. So they weren't too worried about this. They didn't deem this to be a failure of meeting the spec because the test was really excessively harsh. But it's good to do this, right? Because this is basically a test to failure. Figure out where the problem is. This plot shows what happens if the control path delay is too long. Now, when we were doing this kind of thing, the BIS has to measure the frequency, measure the voltage, take those signals, process them, know what to do with them, take an appropriate response, so on and so forth. Well, as you know, what if I'm using a meter that isn't giving me a message continuously, which of course they don't, they're digital. So, like the Schweitzer relays, the synchrophaser data can come to us at 60 messages per second. It'd be a pretty fast messaging rate. But there are a lot of meters out there that are much slower than that, like maybe just 2 or 3 messages per second. What happens if I build that kind of delay in the path? Well, what you see on the screen there is what happens. You all know, most of you have at least some engineering background, you know what happens to a high gain control system if I add path delay. It reduces the stability. It starts to get oscillatory. And that's exactly what happens here. Remember I said that BIS is fast. That's the high gain part. If there's too much delay, you notice that this system would tolerate 25 or 50 milliseconds of delay and still damps out and looks pretty good. But at 100, we breached the 60.5 and 59.3 hertz limits. And at about 250 milliseconds, the system actually became unstable. It couldn't recover the steady state. So you have to pay close attention to the design, the implementation of the controls. It's not just the software. There's also practical applications like control path delay. Remember, the delays include the filtering. There's all kinds of signal filtering in there too that has to be considered as a part of the delay path. So we've already hit most of these. The key lessons learned were that you can make these seamless transitions. There's several ways to do it. We did it by doing it with the droop controls all the time. We achieved the seamless transition between BIS control and generator control. There was a lot of benefit to keeping the BIS in droop mode while recharging. I'm going to talk about accommodating some PV here, but we also talk about the control path delays. You've got to keep the control path delays short. So I mentioned, okay, a lot of people want to add solar to their microgrids for extra resiliency. What does the solar do for you? You see the second bullet here? It reduces your fuel usage. There's a, I won't call it a standard because I don't believe it's in any way mandatory, but in the Northeast, there are some requirements that are being suggested for how microgrids should be configured in order to make them most beneficial for situations like this. And one of the things they're encouraging is they want you to have at least 14 days of off-grid autonomy in your microgrid. And if you think about it, that is a long time. Well, solar can be a huge help in helping you meet that goal because the fuel source is on site. As long as you got sunlight, it'll just run forever. So the PV technology itself also tends to be extremely reliable. The modules are tough. So it's a good thing to have around in a storm situation. They've been proven very robust in hurricanes and a bunch of other things, although we've lost them in hailstorms from time to time. But the question was asked a minute ago, okay, well, how much PV can you accommodate? That question, I think, was specific to a distribution feeder. The slide I'm showing you right now is specific to a low inertia system, so it's a little different. But the concept is the same, that for microgrids or low inertia systems, if your PV penetration is less than 10% of your total microgrid generation, disappears into the load. You don't see it at all. So you don't have to do anything. Between 10 and 30% penetration, you will start to see some impacts on your generators. So you may have to do some retuning. Load controls would be good. Under frequency load shedding can be extremely helpful. One of the things you got to watch for here is mass tripping events. In other words, we have a situation where you've got a loss of generation, so the frequency drops, or a fault followed by a fault clearing. So the frequency drops during the fault, then overshoots during the clearing. You can breach those frequency trip limits, and then you'll lose all your PV, because again, frequency is across the whole system. Whoops. So you have to adjust your trip thresholds to make sure that the inverters aren't all tripping at 59.3 hertz, for example. Fortunately, with modern inverters, that's pretty easy to do. Just widen the trip set points. One other thing to watch for, too, is minimum loading constraints on your engine gen sets. That can become a serious issue as PV penetration goes up. Between 30 and 50%, now the PV has to act as a system asset. There's enough of it there that it's going to kick your grid all over the place if you're not properly using some of these grid support functions we talked about. And if your PV penetration is above 50%, you start questioning the definition of a distributed generator. You got more PV than you got diesel in there now. So above about 60%, you almost have to have storage to run the system stably because you don't have enough generation to recover the system if something happens and the PV drops out. So this is, again, your question was more specific to a distribution feeder, but this is the slide I was telling you about before. How do you mitigate this? One of the big things is use the right inverters. You got to have inverters with the grid support functions. You got to have the ability to widen those trip set points. One of the things I wanted to point out here is when we have tuned generator governors in the past, what we've generally done is we have used what I call a tune and watch approach. If you look at the owner's manual, that's actually what it tells you to do. There's two knobs on there, gain and reset. And those are the P and the I of the PI controller. So you basically just, according to a set of instructions, you tune them until the thing looks about right. And I don't mean to mock that because that's worked well for decades and decades. The problem is now, as I mentioned before, I've got multiple interacting sources. I've got sources with dramatically different time constants. The tune and watch approach simply doesn't work in a case like that. You'll never get the system tuned right. So you really do need quantitative guidance from modeling or something like it in order to get your parameters set correctly. I mentioned before the volt-var function. Here's a frequency watt function for a PV plant. What happens is as the frequency goes up, the PV rolls off because frequency rises during an overgeneration condition. So have the PV back off to help assist in the overgeneration. Now you notice if the frequency falls, that's undergeneration. What we would really like is to have the PV ramp up, and of course it can't because it's already at its maximum power point. It doesn't have more power to give us. So what happens is we want it to hold in there for as long as possible. And at some low frequency, we're going to say, look, something's wrong, and the PV is going to trip. That's what that vertical drop is. But what you'll do is that push that F low 1 as far to the left as you can so the PV hangs in there. I'm going to gloss over a couple of these a little bit. Can you do PV without storage? Right? If you're talking to your local Target store, they've got a 500 kilowatt array on the roof. They've got no backup generation, no storage. They want to say, hey, during a blackout, can I use that as my backup power source? The answer is, well, technically yes, but it's a very difficult thing to do. You got to have the right inverter again, but you have to have really fast load shedding because I got to get the load below the generation. And of course, the generation's changing. So there are some ways that you can deal with this, and we won't have time to talk about them now. Anybody who's interested, just contact me. And of course, you don't have any power at night. So most customers, when they look at this, say it's not worth the hassle. Could I do PV with storage? No diesel gen set. Oh yeah, sure. We do that all the time. We've got lots of off-grid systems that look like that. They're particularly good in storm recovery because they don't have to ship in fuel, right? The fuel's coming to me from the sky. So that's kind of nice. Remember that what the PV does is it buys you that extended off-grid time. The storage is what buys you the reliability during the shorter outages. So actually, lots of times, the storage by itself is all they really need. They don't need the PV if your average outage duration is sufficiently short. But again, the real key is you've got to have a lot of load controls. And I wanted to show you this slide here. There's a classic example of an off-grid PV system where PV is the economical choice. This particular one is in Cherry County, Nebraska. But you see we've got PV running a small instrumentation package. But the deal that I wanted to show you here is that if you're looking for those last few nines of availability, the relative cost of the system starts to shoot up if you're doing it with only PV and with no engine genset. The reason is because if I've got 4 nines, let's say, and I want to get that 5th 9, well, in order to do that, I've got to be able to ride through a certain number of overcast days fully recharging my batteries. How do I do that? Well, I make the PV array bigger. So I have to really oversize the PV, meaning that most of the time it's going to recharge the batteries in 2 hours and then sit there for the rest of the day. So I've got this massively oversized PV system trying to grab those last few nines of availability. For a small plant like this, no worries. The load's small enough that we can afford that kind of overdesign. But if it's a big enough load, you'll have PV for energy, but an engine genset for reliability. What we call a hybrid plant. And of course, don't forget about protection. I've mentioned before that with a lot of these systems, we're seeing more systems that are inverter-dominated. And I mentioned that inverters are very strongly current controlled. What happens in a case like that is you don't have enough fault current that you can blow fuses or that you can reliably use overcurrent protection to sufficiently protect the system. Sometimes you can, because some battery inverter systems will have a function in them so that they source a lot of fault current. You've got to be careful. The inverter has to be sized for it, right? There are some cases where the battery inverter system might be significantly over-designed relative to the load, so that your maximum load current and your load current and your fault current might be far enough apart that there's still room to put TCCs in the middle. Sometimes you can get away with it. But if that doesn't happen, you really got to pay special attention to the protection aspects. And that's one of the areas in which our firm specializes. So if you run into a situation like that, please call me. Commercial. Last thing I wanted to talk about very briefly is the modeling of systems like this. And we're short on time, so I'm going to have to go fairly quickly. I've already talked about this quite a bit. The pros of the modeling are pretty self-explanatory. It really improves your understanding, reduces your risk, reduces your overall cost. It's a very good thing to do, but modeling ain't cheap. It's expensive to do. The data needs are very high. You've got to have validation of some kind. How do you know the model's not lying to you? So you got to have something to prove that. And you need someone who knows what they're doing. Unfortunately, I've seen a lot of very reputable companies produce models that when we started looking at them, we thought, that doesn't make any sense. And when we dug into it, it was because the model was wrong. So you need people who know how to catch those things. I think this is pretty self-explanatory as well. When the modeling is most useful, really, is when you have a very complex system. Simple systems with one generator, one set of loads, you don't really need modeling for that. Or you can buy one of those off the shelf from Generac or Caterpillar or somebody like that. But if you've got a complex system with multiple network sources, inverters plus rotating machines, batteries plus other things, that's when you really got to start to look at this. Also, if you've got a really critical situation in which you can't put it in the field and then adjust it, it's got to be right when it goes in. An example that I threw in here is if you got a grounding transformer, but you start getting false trips. Right? Remember we talked about this, trying to size the grounding transformer to make sure that it's not throwing the DG offline all the time. We really need to get that right in the first place, because if you get it wrong, what's your option? Put in a different grounding transformer. We have to do the whole process again. So you really want to get that right in the first case, and modeling can help with that. You need to use the right type of model. And this is where I was going to break this down for you a little bit, that a lot of the standard models that we use, things like Sine Synergy, Aspen One-Liner, these fall into the category that I would call calculation automators. They're not actually simulators. What they do is they take a standard formulation of a problem, you dump in your parameters, and they solve it for you. So really what it is it's kind of like a macro. And understand, I'm not putting that down, because as I mentioned before, for 80%, maybe 85% of the calculations that we do, there's a reason why those are standard calculations. It works just fine. So most of the time, that serves your needs. It's that other 15%, you got to know where that 15% is. For big system simulations, like if you're trying to simulate the entire Eastern Interconnect or something like that, you would use a simulator like PSSE or PSLF. These are sometimes referred to as electromechanical simulators. They are phasor domain simulators. They are time domain, but using a phasor representation of the system. Then we get to the full transient dynamic simulators. And this is the kind of simulation we do. We actually do PSSE as well, but most of what we do, our main workhorse is MATLAB Simulink. We also use a bunch of different variants of EMTP. What these simulators do is they actually are looking directly at the differential equation representation of the system. So in theory, this is supposed to be the most accurate, least assumption physical model of your system. Then the different programs have different solvers that they use to execute the thing in different ways. So in theory, as you see that I've got this in blue here, the minimum number of assumptions, theoretically the maximum physical fidelity from something like this, and the maximum flexibility, maximum breadth of applicability, but also the maximum input data requirements and its higher cost, because it takes time to get these models up and running and interpret their results. And then the last one is a steady state simulator. I listed the OpenDSS there. OpenDSS is a really powerful tool if what you need is a series of snapshots. I've got an 8760 simulation in there. There's 8,760 hours in a year. If somebody says I've got 1 year's worth of hourly solar data, 1 year's worth of hourly load data on this feeder, put a PV plant here and tell me how that's going to impact the voltage profile at each of those hours during the year, OpenDSS is your tool for that. You can do it in MATLAB Simulink. Probably take you 2 weeks to run it. OpenDSS will do it in 20 seconds. I like to show this slide because, well, why doesn't everybody do simulation? Simulation is so great. And the reason is because what this graph is showing you is you see we've got a perceived value and cost on the vertical axis and the level of abstraction on the horizontal axis. 100% abstraction is pure simulation in the computer, and then I get towards 0%, which is actual hardware on the actual system, noticing that hardware testing in the laboratory is not 0% abstraction. It's very important to remember. But what you see is that the perceived value drops below the cost when I get to 100% abstraction. The argument that I would make is this one. This is what people are forgetting. What does the simulation give you? There's a tremendous amount of understanding that's gained. And the reason largely is because in simulation, almost everything is observable and controllable. For those of you who have worked with field data, how many times haven't you had an event on your system, then you are handed reams of data, you're asked to find out what goes on, and then you spend months in weekly 2-hour meetings, after which you finally shove the data back across the table and go, oh, we don't know. We can't tell. There's not enough here. With simulation, again and again and again, we found this case where there's some head-scratcher problem, and we run it through the simulation, we work with it for a while, we collaborate with the people who have the system, and at some point, you get that, aha, I see what's going on. I get it. Then we can engineer a solution. So that's what simulation does, is it dramatically improves your level of understanding. So I'm not going to go through this example. It's in your notes, but what we're going to do is, I was talking specifically about GFOV. We run through a model, a case where we're actually modeling one of these things in MATLAB Simulink. I'll show you this slide right here because I mentioned validation results. I love to show this slide because this is one of the very best validation results I have ever had in my life. But you notice we modeled the thing, then we actually ran an experiment. We nailed the level of overvoltage pretty much spot on, less than 1% error. That's pretty good model validation. So we're very confident in this one. Usually, if you're within 5, maybe even 10% under the circumstances, we're going to call that good. This one was really, really good. So then we test it up and model it, and we mentioned this before too, that if you're going to be doing anything with low inertia systems, the modeling is incredibly, incredibly valuable. So it's a good thing to do. So I thank you very much for your attention. This, by the way, that's the solar array that we built in Wrangell-St. Elias National Park, right there. The very last slide, I haven't gone to it because I like to leave the picture up, but you notice that my email address is on there. Do not hesitate to drop me a line if you have a question that you'd like to follow up with, or if one of the papers I mentioned is of interest to you. Other than that, thanks very much, and I'll take any final questions before we shut down. I haven't heard a single forehead hit the table yet. So, how about you remote folks? I don't know if I can see everybody. There may be some people hiding just beyond the camera. If they are, wake them up, please. All right. If there aren't any questions, then thanks. Thanks a lot, everybody. Appreciate it, and we'll talk to you again soon.